We're in Rosen, Discrete Mathematics and its Application, section 9.4. In this talk, I'm going to show how to demonstrate that 2 is a primitive root of 11 using a table method. So first I will need to create the table of I values. Remember, if something is a primitive root, then every integer of the under less than the prime that the root is raised to will return something different, something unique from the set of integers, positive integers less than the modulus. So here I will take 2 to the I mod 11, and that is what I want to demonstrate, that 2 is a primitive root of 11. So I'll create some table columns here, and then 2 to the first power mod 11 is of course 2. 2 to the second power is of course 4. 2 to the third power is of course 8. And 2 to the fourth power is 16, which mod 11 will be 5. Now as these numbers get larger and larger, to do them directly it gets more and more challenging, but we can take advantage of the fact that 2 to the fifth mod 11 can be replaced by 2 to the fourth mod 11 times 2 to the first power mod 11, all mod 11. You'll remember that from an earlier portion of the chapter. So 2 to the fifth mod 11 is 2 to the fourth mod 11, which is 5, times 2 to the first mod 11, which is 2, and that's 10. 2 to the sixth mod 11 is 2 to the 5 mod 11 times 2 mod 11 mod 11. So that's 20 mod 11, which is 9. 7 then will be 2 to the 7 will be 2 to the 6 times 2 to the 1, all mod 11. That's the same as 9 times 2 mod 11, which is 7. 8 will be 2 to the 8th will be 2 to the 7 times 2 to the first, all mod 11. Well, that's going to be 2 times 7 is 14, mod 11 is 3. 2 to the 9 will be 2 to the 8 times 2 to the first, all mod 11. That's going to be 6. And we could do 10 a couple of ways. 2 to the 10 mod 11 is 2 to the 9 times 2 to the first, all mod 11, which is 12, which has a remainder of 1 when divided by 11. Of course, we could also use Fermat's little theorem. Since 11 is prime, 10 is 1 less than 11. 2 is relatively prime to 11. Well, Fermat's little theorem says that is 1. And since I have a unique mapping, a one-to-one and onto mapping from the numbers 1 to 10 to the numbers 1 to 10, I have a primitive root of 11. And now I want to talk about the concept of discrete logarithms. We can use this table to calculate the discrete logarithm of base 2 of all possible values less than 11, all mod 11. Okay, so the way this will look is we're going to take the log base 2 of I, and it's with respect to the modulus of 11. So what do we raise 2 to? What power do we raise 2 to get 1 in this range? Well, it'll be 10 because of Fermat's little theorem. 2 to the 10 mod 11 is 1. What number do I raise, what power do I raise 2 to in order to get 2? What's going to be 1? 2 to the 1 is 2. What power do I raise 2 to get 3? Well, I look across here and I see that 2 raised to the 8th power is 3 mod 11, so I put 8 here. What power do I raise 2 to get 4? That's going to be 2. What is the power of 2 to give 5? Well, remember that was 4. 2 to the 4 is 16. mod 11 is 5, so I've got to raise 2 to the 4th power to get 5. What do I raise 2 to get 6? That's 9. What is the power of 2 that gives 7? It turned out to be 7. This column's all the same. What is the power of 2 to give 8? Of course, it's 3, mod 11. What is the power of 2 to give 9? It is 6. What is the power of 2 to give 10? We see that it is 5. I'm going to write down 5 here. So the discrete logarithms, as you can imagine, for a much larger number would be rather tedious to do this way. And it turns out there isn't really, there is not an efficient algorithm known to quickly calculate the discrete log. We basically have to do what we've just done. And because of this inefficiency, it can be used very effectively for certain types of cryptography, which we'll look at in section 4.6. So that is how you use the table method to determine whether a number is a primitive root, and then to use that table to find discrete logarithms.